For today's task, I asked you to modify yesterday's combination lock program to set up a slightly different version of a combination lock. Yesterday, we broke the lock by guessing first column 1, the first digit, lock 1, and then column 2, the second digit, lock 2, in order. We found that it took about 2 to 3 pushes of button A to guess the first number and 2 to 3 pushes of button B, for a total of about 5 overall pushes to break the lock. Today, instead, I asked you to write code where you would have to guess lock 1 and lock 2 simultaneously when you pushed button A. You'll notice that today's code is fairly similar to yesterday's code. You're using very similar statements. For instance, the start statement, setting things up, lock 1 and lock 2 are generated from random numbers. Those are identical. The difference is, whereas yesterday when button A was pressed, you would guess the first number, and if you were correct, you would plot it to screen, and then you would move on to button B. In today's code, when button A is pressed, you have to guess both numbers. You have guess 1 and guess 2. And you only plot the numbers if both guesses are correct. So you need, as I mentioned in the introduction to today's task, you need an AND statement to combine these. You have to get both guesses, 1 and 2, and then plot them up. So let's run today's version of the combination lock program and see how many guesses it takes for us to break the lock. So here we go. 1 guess, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So it took 24 guesses this time around to break the lock. Many, many more guesses than were required yesterday. Let's try that one more time. Hopefully it won't be quite as long this time. 1, 2 guesses. So you can break it quite quickly. It turns out that on average, if you were to get a room of students together, a couple of dozen students trying this themselves, and you would plot up the number of distributions, you'd find that on average it takes 12 to 13 guesses to break this lock, whereas yesterday it took about 5 guesses. If I'd extended this problem and said, well, why don't we try and make a 5-digit combination lock and see how long it would take to break that? Obviously it would take much longer unless you automated it and got the microbit to just print out how many steps it took in breaking the lock, how many guesses it took. But for yesterday's lock, where once you guessed A, you could move on and guess B, and then column 3, C, and then column 4, and then column 5, it would have taken 12 to 13 guesses on average to break the full 5-digit lock. Whereas for today's problem, it would take over 1,500 guesses, today's version of the combination lock. Much, 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 much more effort. And in fact, there's a simple mathematical relationship. You've probably already thought about it. And it's just that to break yesterday's lock, you require 5 plus 5 divided by 2, which is 5 total guesses. Today's is 5 multiplied by 5 divided by 2, so 12 to 13 guesses. So breaking a combination lock in order is much, much easier than it is to break the whole thing at once, which is obviously why password crackers don't let you, unless you watch some very old movies, passwords don't let you break the first digit and then move on to the second digit and tell you, yes, you've got it right. You have to break the whole thing at once. From a computing perspective, I want to highlight again that we used very similar statements today as we did yesterday. What changed was the order in which we executed these statements. This is sometimes called control flow, how you control what is happening inside your program. This hints at the power of computing. If you can take a few simple statements and by ordering them differently, achieve quite different results. You can address a wide variety of problems, and that's a very powerful thing to be able to do using just a few statements. Finally, I want to show you the solution for these stretch goals that we discussed at the start of today's session. I mentioned that it might take a while to crack this version of the combination lock, and so perhaps it might be nice to show the user, the person running the program, what they'd guessed every time they pushed button A. So here's a version of the code that does that. We still have the same setup. We're still going to set up a lock to guess to try and break. And when button A is pressed, we're still going to have some guesses. And if those guesses are both correct, we're going to plot some things to screen. I've created this variable guessed. And I've said, okay, guessed is false. Only if guessed is true are we going to proceed. And so this allows us to stop the program. It means that nothing will happen to the lights once the answer is correct. And also, I initially, every guess, plot the guesses in columns 0 and 1, the first and second column of the microbit display. And then, if I get things right, we're done. Guessed is true, and I plot the right answers. But otherwise, we keep going, but I'm going to have to unplot the LEDs so we can have another try. So I didn't necessarily expect you to work your way all the way through this logic in 30 minutes, but I did want you to see a possible solution, and if you like, you can think about it more after the session. But let's at least play this version of the combination lock and see what happens. When we press button A, we see our guess. Notice it vanishes after about a second, 1,000 milliseconds, and it vanishes because we unplot our guesses. Let's have a third guess, a fourth guess. So you now get to see the guesses we're making. When we get the guess correct, as we did here, additional columns illuminate, demonstrating that we are correct. And at this point, when this happens, if we got it correct, if guess 1 equaled lock 1 and guess 2 equaled lock 2, if both were true, we plotted some additional columns, 3 and 4, the guesses, and of course guess corresponds to lock here because these are equal, so this is the correct answer. And then once that happened, we set guessed to true. Now that guessed is true, when button A is pressed, nothing will happen. As you can see here, we're locked in state because I made it the case that I forced it once we got the right answer to not execute this if and there's nothing else to do. This again highlights a little bit of control logic, this idea that once guessed is true, we default to a different state where we're not going to execute any of these statements. So the order in which you execute statements and the state of various variables can control what is displayed on the microbit.